Hello learners, welcome to this course on Arduino Mega Board programming and simulation. In this video tutorial, I will be discussing about on how to interface a servo motor with Atmega 2560 microcontroller. So first let us discuss about the basics of your servo motor. So servo motor is widely used whenever we require the rotation with great precision. So if I want to move the shaft to a particular position, then we can achieve it using your servo motor. Whereas in a DC motor, what happens if I switch off the power supply also, it will make some revolutions before it stops. So there we would not be able to get an accurate positioning when I try to use a DC motor. Whereas a servo motor, we can achieve this shaft positioning to a greater precision. So depending upon the power scheme, whether it is a AC or DC given to a servo motor, we can term it as DC servo motor or AC servo motor. So here I have shown a picture of your MG90S servo motor. So here it comes with different types of shaft which can be connected to this servo motor. And you can see it has 3 leads. So in the 3 leads, one lead, orange color line, it will be for your PWM signal. PWM is pulse width modulation signal. And red line will be a supply voltage and brown or black will be your ground line. So this servo motor shaft positioning depends upon the PWM signal, pulse width modulated signal. So before moving on to this, we will try to discuss the internal architecture of your servo motor. So here I show the internal architecture of your servo motor. So the servo motor essentially consists of a DC motor. But now the DC motor is connected in a closed loop system. So closed loop system in the sense, the speed of the DC motor is reduced using this gear mechanism. So, and the position of the shaft is measured using a sensor, either using a position sensor or using a potentiometer connected to this gear mechanism. So, thereby I get a signal based upon the shaft position, and this shaft position is compared with the input from the user to which position we want our shaft to move. So based upon these two signals, so this reference output signal is from the actual position of the shaft and the reference input signal is from the user to which position we want the servo motor shaft to go. So the difference between these two signals will be given as an input to your DC motor for adjusting the position of the shaft. Once the shaft position and the user input position are same, the error signal will be 0. In that case, we will not adjust any value to the DC motor, thereby the shaft will remain in that position. Again, whenever there is a change required in the shaft position, the user input signal will be given and it will be compared with the current position of the shaft, and the error signal will be given as an adjustment voltage to your DC motor, thereby the position of the servo motor will get changed and it can able to retain a proper position. So the important thing to note here is the servo motors, it doesn't rotate at a faster rate when compared to your DC motor. The speed reduction is done by this gear mechanism, and also the positioning of the servo motor happens through this closed loop system. So in order to get the positioning of a servo motor shaft, we need to generate the PWM signal. PWM is nothing but pulse width modulated signal. So here I show a typical PWM signals. So PWM is nothing but we will be generating a square wave with a certain duty cycle. So the duty cycle is nothing but total on time out of the total time period. So here if I see T on plus T off is nothing but the total time period. In T on plus T off, 50% of the time I have a on time. So which means it is a 50% duty cycle. In the second case, in signal B, again this period is same, but the on time is only 10% of the total period. So this is called as 10% duty cycle. In the third case, signal C, in the total time period, for the 30% of the time, we have a on time. Again, in the fourth case, we have 70% of the time, we have on time. So depending upon this pulse width, the shaft position can be varied. So for example, here I have shown a parallax servo motor and its timing signals. So here this parallax servo motor will rotate 180 degrees from minus 90 to plus 90. So few servo motors can rotate 360 degrees and it will be little bit costlier. So if I take a 180 degree movement servo motor, so if I want my servo arm to get positioned in minus 90 degree, then my on time of a pulse should be 600 microsecond. If I want my servo to move to 45 degrees, then my on time of a PWM signal should be for 1050 microsecond. For 0 degrees, I should give an on time of 1500 microsecond. For plus 90 degree, I should give an on time of 2400 microsecond. So what is the minimum resolution which we can get through the servo motor is 1 degree. So for getting 1 degree variation, we can make a simple calculation. The total time difference from minus 90 to plus 90 is 2400 microsecond minus 600 microsecond, which is 1800 microsecond. So 1800 microsecond on time variation for 180 degrees. Then for 1 degree, it will be 10 microsecond. So if I want to get something like minus 60 degree here, minus 60 degree. So minus 60 degree means here minus 90 to minus 60, I have 30 degree variation. So 30 degree means 30 into 10 microsecond, which means 300 microsecond variation. So that 300 will be added with your 600 microsecond, which is nothing but 900 microsecond. So if my on time of a pulse is 900 microsecond, then we will get the shaft position to minus 60 degree. And the total time period remains fixed. So it will be 20 millisecond. In few servo motors, this timing can be varied, something like this. So it can have an on time of 1 millisecond out of 20 millisecond. Then the shaft can be positioned to 0 degrees. If I have an on time of 1.5 millisecond out of 20 millisecond, then the shaft can be positioned to 90 degree. If the on time of 2 millisecond out of 20 millisecond, then the shaft can move to 180 degrees. So it is better to look at the data sheet of a servo motor before deciding on the on time. So few servo motors works with this type of timing information for on time. Few servo motors will work with the below part. For 0 degree, we have to give an on time of 1 millisecond. For 90 degree, 1.5 millisecond. For 180 degree, 2 millisecond. So now let us discuss about how to interface the servo motor with Atmega 2560 microcontroller. So we are going to use a Arduino IDE for writing our embedded C program, and we are going to build the circuit and simulate the circuit using Proteus 8 environment. So now in this tutorial, I will be discussing about two cases. One is I am going to connect just a servo motor to a Arduino Mega Board. So by default, we will try to move the position of the servo motor from the Arduino Mega Board. In the second case, I will be using a potentiometer connected to a Arduino Mega Board, and depending upon the potentiometer value, we are going to adjust the position of your servo motor. So in the first case, we are going to vary the position of your servo motor automatically by the program running on a Arduino Mega Board. In the second case, depending upon the potentiometer value, we are going to change the position of your servo motor. So we will discuss both aspects in this tutorial. So first, let us build the circuit. So for building the circuit, I open Proteus 8 environment, create a new project, select the location where we are going to put the new project. So I will create a new folder, Servo Motor. Select it. Then use a file name for saving your project. I will give it a Servo Motor with an extension of .pdsprj. Press next. We need to use a default schematic. Press next. We are not going to use any PCB layout. Press next. I am not going to use any firmware. So press next. So we have selected only the schematic. We are not going to use any PCB layout or firmware. So press finish. So it will open this window. So first thing we need to do is we need to select the items which we require for our circuit building. So go to pick device, type Arduino, add Arduino Mega Board to your list. Then I require a servo motor. I select the PWM based servo motor, add it to the list, and we also require a potentiometer. I'll put a pot. I will select this potentiometer HG, which is having linear, log and anti-log variation. Press it. So these are the items which we require for this project. So we select the components, press OK. So now we use this component to build the circuit. So Arduino Mega Board, I place it onto the circuit. So when we look at our circuit, I am going to connect the servo motor to pin number 9 and potentiometer to A0. So we are going to do both the things in this tutorial. So we need to connect the servo motor PWM9 to pin number 9 of Arduino Mega Board and potentiometer to A0. So I take potentiometer, put it onto your schematic and connect it to pin number 9. Sorry, not 9. We need to connect it to A0. So I will place this potentiometer below so that it becomes easy. So connect this potentiometer to A0 line or ADC channel of your Arduino Mega Board. One end of the potentiometer I am going to connect a supply selected from terminals mode. Connect the supply. Another end I am going to connect the ground. So ground is also available in the terminals mode. Then we are going to connect the servo motor to pin number 9. So go to components mode, select the servo motor, place it onto your schematic. So here in the servo motor, the center line is your PWM line. So connect the center pin to the pin number 9 of your Arduino Mega Board. So other two ends are supply signals for your servo motor. Go to terminals mode, select power, place it onto your schematic, connect the power to your servo motor and ground to the other lead of your servo motor. So this completes our circuit part. Let us save the circuit. So we have connected a potentiometer and a servo motor connected to pin number 9. Save the circuit. Now let us go and do the programming part. First let us take the case 1. So in case 1, in order to activate your servo, we have a library function already embedded into your Arduino IDE. So you can check what are all the libraries available in file. You can go to examples. Here you can see different libraries. So already a servo library is included and a sample example also is given. So in order to use that servo library, I just use this command #include servo.h. Then in order to name and servo, we give the name myServo for this servo keyword. Then I am going to initialize a variable position with the 0. And we need to say to which pin we have connected our servo motor. So that configuration part we are going to do it in the setup function. So myServo.attach will make our pin number 9 is connected to your PWM line of your servo motor. So this completes the configuration part. And in the loop part, we write the logic which needs to be executed infinite number of times. So here I use a for loop, initialize the for loop to 0 position, and I am going to check the condition of position whether it is less than 180, and I am going to do incrementation for every iteration. So inside this for loop, I am going to write the position to your servo motor. So when the for loop runs for the first time, my position will be 0. So my servo will go to 0 degree. When the for loop runs for the second time, it will be incremented. The position will be incremented by 1. So position will be 1. So it will go to 1 degree, 2 degree, 3 degree. So like that it will keep a movement from 0 degree to 180 degree. Once it reaches 180 degree, it will come out of the for loop and we are going to execute the second for loop. So here first we initialize the position to 180 and I am going to check whether the position is greater than or equal to 1 and I am going to do decrementation for every iteration. So here we try to change the angle from 180 degree to 1. Since this is a loop function, again the servo motor will go from 0 to 180, from 180 to 0, 0 to 180. So like that it continues its motion. So this is the case 1. So let us try to execute this case 1 and try to see it. So let me save this program. It as case 1 dot C. The program should be saved with an extension of .c. Save it. Then to compile and convert this program into a binary code, go to Sketch, export compiled binary. So it gets compiled and you can see the corresponding hexadecimal file. When you open this, you can see this is the hexadecimal file which we have created. Now this hexadecimal file, we need to import it into your program memory of Arduino Mega Board. So go to Proteus, right click on Arduino Mega Board, edit properties, select the program file. Select the program file. So we have imported our hexadecimal file into the program memory of your Arduino Mega Board. Now we have to check. So in this case 1, we are not using the potentiometer. We are using only the servo motor connected to your Arduino Mega Board. So when I press, you can see it goes from position to 180 and again it will come back to 0. So it keeps on continuing this operation. In the second case, we are going to make use of the potentiometer. So the potentiometer value will decide the angle of your servo movement. So let us discuss the programming part. So as usual, we include the header file servo.h and we name our servo to be my servo and initialize the position to 0 using a variable. And I am going to use another variable called as sensor pin and it is initialized to A0 where we are going to connect our potentiometer value, and I am going to use another variable called sensor value and it is initialized to 0. So as usual, the configuration part takes care in your setup function. So here I specify where we are going to attach our servo motor. So we are going to attach the PWM line of your servo motor to pin number 9 of your Arduino Mega Board. Then in the loop function, we are going to read the sensor pin. So sensor pin is nothing but A0. So we are going to read the analog value in pin number A0 and it will get converted into a digital value. Since we have a 10-bit ADC, my value in the sensor value variable will be between 0 to 1023, because 2 power 10 is nothing but 1024. Since the value starts from 0, it ends at 1023. So our sensor data will be between 0 to 1023. So in order for our PWM to be generated, we need to convert this 0 to 1023 data to 0 to 180 degree. So for that I use a map function. So I give the sensor value. So my initial value is 0 to 1023. It should be mapped to 0 to 180 degree. So thereby we can get different position of your servo motor. So once this mapping takes place from 0 to 1023 to 0 to 180, then I send that value to my servo motor. And this continues. So as I change the potentiometer value, the value read by our microcontroller will change. Thereby the value sent to the servo motor will change. Thereby the position of the servo motor gets altered. So again, let us save this program. So let me save this as servo motor case 2. .c. Save this. Once I save this, I can compile it, export compiled binary. So it will get converted into a hexadecimal file. Once we have converted our hexadecimal file, we can import this file into your Proteus 8 environment. So we can go and right click on this Arduino Mega Board, edit properties. So here let me select the program file. So we are going to select the case 2. Hexadecimal file. It gets imported onto your program memory of your Arduino Mega Board. So now let us run this program. Now we see the servo motor is in certain shaft position. So if I change the potentiometer value, you can see the position of the shaft gets altered. As I keep on increasing, the shaft position gets altered. Same way, if I decrease, the shaft position gets changed. So by varying the potentiometer value, we are adjusting the shaft position of a servo motor. So in this tutorial, I have discussed about on how to interface a servo motor with Arduino Mega Board. So we have discussed about two cases. One is directly giving the logic from our microcontroller, and the second case, depending upon the potentiometer value, we try to adjust the position of your servo motor. So thanks for watching. Please subscribe for more technical learning. Thank you.